Hi. In the preceding video, I introduced valence bond theory, which says that bonds are made via the overlap of atomic orbitals. And we saw a couple of examples. Mainly they were diatomic molecules like H2 or F2. But in many cases, especially if there's a central atom in the molecule, the orbitals s, p, and d aren't really the ones that are making the overlap. Instead, we're going to look at what's called a hybrid orbital. Now, orbital hybridization is just a fancy word for mixing, and we are going to see how atomic orbitals can mix to make these hybrid orbitals because, like I said, in the vast majority of cases, it's not the atomic orbitals sp and d that are overlapping, but it's these new type of hybrid orbitals. And we'll do plenty of examples because it is kind of an abstract, at first, concept. But I think you'll realize that when we do this hybridization of the orbitals, things are going to fall into place, especially molecular geometry and bond angles and the number of bonds. So it's a very important topic, and I'll guide you through it. The first thing is this word hybridization. Hybridization is the mixing of atomic orbitals in an atom to create what's called hybrid orbitals. And it's these hybrid orbitals that are going to follow valence bond theory. Okay, so we are still using valence bond theory, but now we're going to overlap hybrid orbitals. So just as a little note, we will still use valence bond theory. Okay, let me talk about the story of carbon. And I'm going to start out with the Lewis dot symbol. This should be very familiar. You've seen this before. In carbon, the Lewis dot symbol, you were told to put the 4 valence electrons, one on each side. So there are still 4 valence electrons. We've always known that from the electron configuration. Okay, and yeah, what happens here is that you have 4 spots to make bonds to hydrogen. And we know that carbon has 4 bonds in the neutral state. And then we're off to the races, right? We have 4 bonds. I like to think of them as balloons, but you could also think of them as electron domains. And the electron domain shape is tetrahedral. This is all review. And the molecular geometry is also tetrahedral. Okay. So in this case, we're using Lewis structure theory, and the idea, right? The idea that you have a single electron, which is overlapping, or its orbital is overlapping with a orbital from hydrogen, which also has its single electron, and we have 4 of those. Okay, but if we go back to electron configuration, we're going to run into a problem. And the problem is that for carbon, your electron configuration is 1s2, 2s2, 2p2. But when you draw the box diagram, you realize, right, that in the box diagram, you have these 3 2p orbitals, 1s, 2s, and 2p. When we populate those boxes, right, we have 1, 2, 3, 4, 5, 6. 6 total electrons 4 valence electrons. But you notice that we only have 2 slots to make bonds. So really, if we just stick with the electron configuration that we've always learned, or that we've learned before, really, we have those 2 valence electrons as a pair, and these 2 electrons that are unpaired. And it would have been predicted that we could only make 2 bonds to hydrogen. Okay. But that's not true, and you know that's not true. We don't have this as a molecule for carbon and hydrogen. So that was a dilemma, right? This is question mark. Because we know that carbon has 4 bonds, it's tetrahedral, it has still 4 valence electrons, it fulfills the octet rule. Everything that we've learned, this looks good to us. But if we strictly use valence bond theory and just use the atomic orbitals, it starts to fall apart. So how do we resolve this? How to still use valence bond theory to do what? To get what we know to be carbon with 4 bonds. Okay. How do we do this? The thing is, the atom carbon goes through hybridization. Let's draw the orbitals on an energy diagram, and we're only going to look at the valence orbitals. Now the 2s orbital is slightly lower in energy, slightly more stable than the 2p orbitals, and I'm going to draw the 3 2p orbitals. They're in the direction x, y, and z. Okay, and these are the 2p. If we populate these orbitals, okay, with electrons, I'll use dots. We have 4 valence electrons, 2 and the 2s, and it doesn't matter where you put the other 2, just make sure that they are in different p orbitals because we're using Hund's rule. You singly fill before you doubly fill. And what I have drawn right here matches what I have up here for the box diagram. And we understand that led us astray. It only has 2 openings for bonds with hydrogen. What happens with carbon, and in this molecule, it's called methane, CH4, is that the atomic orbitals mix. They hybridize. So we got to be very, very strict with our terminology. These are atomic orbitals. And we're going to get what's called hybrid orbitals, a mixture. And there's a rule that we got to be aware of. It's sort of like the conservation of orbitals, is that if you mix x number of atomic orbitals you get the same number of hybrid orbitals. And we are going to mix all 4 of those orbitals. And the way I show it is I'm going to put a dotted circle. I'm going to mix all 4. So according to this rule, in pink, we should get 4 hybrid orbitals. Not only that, we get 4, all 4 are going to be of equal energy, and all 4 are going to be like the average of these 2 energies. One more stable, one less stable. So I'm going to draw the 4 hybrid orbitals on this line right here, in between. This is done in real life using Schrodinger's equation. We've talked about the wave functions a little bit. We're not going to get into the math at all. It's just that mathematically you can combine these 4 atomic orbitals and the equation will spit out 4 new hybrid orbitals. Now I draw the hybrid orbitals as lobes, teardrops. Technically, they're not teardrops. They're kind of like a teardrop with a little. It looks like a dumbbell basically, but one side is bigger than the other. But I am going to ignore that. I'm just going to draw teardrops, and don't worry too much about the orientation of the teardrops. But I want to draw one straight up, one down to the left, one kind of towards us, right, and one kind of away from us. Okay, and I'm trying to make them all on the same line. Remember Hund's rule. Hund's rule is that you singly fill all the orbitals of the same energy before you doubly fill them. These are our new orbitals for carbon, and we're going to put in the 4 valence electrons like this. Okay. This is what happens when carbon is in a molecule that bonds 4 atoms, 4 single bonds. And if I put it all together, you're going to see something very familiar. We have, oh, by the way, let me just label this. We have 4. How do we call this new type of hybrid orbital? You just label it with the name that indicates what you mixed. So I literally mixed what? I mixed an S plus a P plus a P plus a P. Okay. We're going to call these hybrid orbitals S, P, and you put a subscript 3 to indicate that you mixed 3 p orbitals and 1 s orbital. Okay. They're in the 2 energy level, but what I mean is 1s, the number 1, the amount, and you have 3, the amount, p orbitals. Now when I put it all together on a carbon nucleus, we have 1 up, 1 to the side, to the left, 1 kind of towards us, and 1 away from us. You see how this looks like 4 balloons? And how do you separate 4 balloons so they're as far apart from each other as possible? Tetrahedral. That's your tetrahedral carbon right there. And if you add the hydrogens have the s orbital, right? 1s. But I'm not going to put the energy level. 1s, s, s. So those are your hydrogens, H, 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 and H, and they each contribute 1 electron to the bonding party. That's your hybridization. And now we can use valence bond theory. Now valence bond theory works. We just had to hybridize the atomic orbitals. And what does valence bond theory say? You have singly filled orbitals on the atom. I almost said atomic orbitals, but these are hybrid orbitals. But they're still orbitals of the atom, and you're overlapping them with orbitals of a different atom, the one you want to make a bond to. And like I said, this is tetrahedral. So let's draw the lines and the dashes in 3 dimensions, and you get a tetrahedral carbon 109.5 degrees. Okay? Okay. That's hybridization, and let me show you a simple problem that you might encounter. It's just state the hybridization. So if I have carbon, and I have those 4 hydrogens, and I'm not going to worry about drawing them in 3 dimensions, so no wedges and dashes. If I ask what is the hybridization of this carbon right here, you're just going to tell me that for that to be true, we had to hybridize all 4 atomic orbitals to make these 4 new hybrid orbitals that are called sp3. That's the name of the hybridization. Carbon is sp3 hybridized. So carbon is sp3 hybridized. And it's no coincidence that an sp3 carbon has 4 balloons. It's not a coincidence that you see literally S plus P plus P plus P. 4 atomic orbitals were mixing to result in 4 balloons of hybridized orbitals. Okay. Another thing, we spoke briefly about sigma bonds. This bond right here will take any of the carbon-hydrogen bonds. That is due to an overlap of orbitals, right? It's due to an overlap of an s orbital for hydrogen and a sp3 orbital of carbon. A sigma bond, if you recall, is when the electron, where the average electron density is along the axis of the bond. And it is a mixture of, or not mixture, but it's an overlap of carbon and, let me see, how do I want to do this? I normally don't put the energy level, but it is an sp3 hybridized carbon. And it is not only that, it's literally an sp3 hybridized orbital that's making that bond. Okay? And it's making a bond with hydrogen and its s orbital. Some textbooks and some people like to put 1s to signify that it's the 1s orbital, but let me stay consistent because I'm not going to call this a 2sp3, okay, even though all of these orbitals are in the 2 energy level. Okay? If you could figure out the number of balloons, you know the hybridization. So here's the trick. Look at ammonia, NH3. So hopefully if I give the chemical formula NH3, you know that your ammonia is trigonal pyramidal. Okay, and if you want to draw 3 dimensions, you use wedges and dashes like this. But what's important here is that you realize that this is also 4 balloons. Hence, this atom, the central atom, is still sp3 hybridized. sp3 hybridized. How is that possible? Well, look what happens when instead of using carbon, okay, and the 4 balloons, I use nitrogen. And my 4 balloons look like this. 1, 2, 3, 4. You know that the electron domain shape of this molecule is still tetrahedral. It's just that the molecular geometry, because we don't have an atom up here, is trigonal pyramidal. This was all discussed when we talked about molecular geometry. How many valence electrons does nitrogen have? Nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. Still, all of these blue lobes are sp3 orbitals. sp3, 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 sp3. It's just that one of them has a lone pair. You see the beauty of this hybridization? Because it allows us to still follow valence bond theory. H, H, H. Those are your sigma bonds right there. So it's a very, I think, a very cool concept, this hybridization. And it helps us explain what we know in real life, that this molecule does have a trigonal pyramidal shape. Okay, you could do the same thing for water, because you know that water has 2 bonds and 2 lone pairs on the oxygen. That is sp3 hybridized. Okay, now what about other hybridization states? I have, oh, here it is. Did you realize that when we look at methane, ammonia, and water, we took care of the tetrahedral family? So this was a study sheet from a previous video. the tetrahedral family. Okay, here, here, and then water would be bent. The main point is that all of those central atoms are sp3 hybridized. What about the trigonal bipyramidal family? Let's look at PCl5. PCl5. Because that's going to be a little bit trickier. Let's do the Lewis structure first. You have P. We're not worried about shape. Right now I'm just worried about Lewis structure. P can have a hypervalency or expanded octet. And this is the proper Lewis structure. Okay. We know for a fact that since you have 5 balloons, okay, that this is what's called trigonal bipyramidal. And we have a P in the center, and we have, now we're looking at shape, 3 atoms that are in this, 3 outer atoms that are in the same plane, the horizontal plane, and 1 chlorine up, 1 chlorine down. And Lewis structures, you want to see every single valence electron, so you do have to draw the lone pairs. And that takes care of all the valence electrons. You could confirm that on your own, right, by counting up the valence electrons for PCl5. The thing is, this phosphorus has hypervalency because it uses the d orbitals. Ooh, d orbitals. So, phosphorus is in the 3rd period. Where's my periodic table? Right there. Okay, so it has 3 s orbitals here. It has 3 p orbitals, but it also has access to the 3 d orbitals, hence the hypervalency. So, instead of drawing the shape, like the sphere for S and the dumbbell for P, let me use the box diagram. Okay, so this is 1s. Oh, no, not 1s. This is 3s. We're only looking at the valence shell. This is 3s. We do have the 3p's, 3p, and we do have the d's, and they're slightly higher in energy. Remember how many d orbitals there are in an atom? There are 5, 3d. But for phosphorus, phosphorus has how many valence electrons? Phosphorus has 1, 2, 3, 4, 5 valence electrons. What we're doing here is we're drawing the box diagram on an energy diagram, energy axis, for the atomic orbitals that are not hybridized yet. Okay, so here are your valence electrons. 1, 2, 3, 4, 5. So if we just stop there with no mixing, okay, with no mixing, then we would only have 3 spots for the chlorine, because these are the half-filled orbitals. But we were able to fit 5 chlorines. What are we hybridizing? We are hybridizing in such a way that we get 5 balloons. We know that if we hybridize an S plus a P plus a P plus a P, that's sp3. And we know that sp3 only gives us 4 balloons. We don't have any more p orbitals, right? There are only 3 p orbitals per energy level. We have to use a d orbital. We're going to hybridize a d. So if you have 5 balloons, that atom in the center is going to be sp3d. 1, 2, 3, 4, 5. And this is hybridized. I wouldn't ask my class to draw the cartoon, the lobes, for sp3d hybrid orbitals. I would expect people to know that if the central atom has 5 balloons, that atom, central atom, is sp3d hybridized, which will give us 5 hybridized orbitals. So I'm going to circle or put a dotted circle around 5 atomic orbitals. Okay, and when we mix those, it doesn't really matter where you put it, but I'm going to put it right here. Remember the conservation of orbitals? You mix 5 atomic orbitals, you get 5 hybrid orbitals of the same energy. And these are called the 5 sp3d hybrid orbitals. Then, right, when you use Hund's rule, you singly fill, because you only have 5 valence electrons, 1, 2, 3, 4, 5. Okay. So what could possibly be another question is that how many d orbitals are unhybridized? Well, these 4 we didn't mix. So you'll just copy them in the same level, or you'll realize, I probably wouldn't ask my class to draw this, but they should realize if I ask how many d orbitals are unhybridized, they'll say 4, 1, 2, 3, 4, and they're empty. Okay. So we took care of all the orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 5 are hybridized. These are unhybridized up here. Okay. I have space. Let me do one more. But again, you should be able to figure out the hybridization of the central atoms just based on the number of balloons. This family was sp3 for each of these central atoms. We just did PCl5, and that's sp3d. But all of these have 5 balloons. So all of the central atoms here would be sp3d hybridized. So what about 6 balloons? Okay, and let's take this one. Okay, let's have a lone pair in there. So you have BRF5, and I'm not going to go through how I got to the final Lewis structure. I just know that the final Lewis structure has this shape. It's square planar. And BR has 1 lone pair. And that's important because that will increase our balloons from 5 to 6. Right there. If you know the number of balloons, 6 balloons, oops, you know the hybridization. The hybridization here is now for this bromine, sp3, which will get us up to 4 balloons. We have no p orbitals left over, so we got to go to the d orbitals. And the Br has access to d orbitals, d2. 6 balloons, s, p, 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 d, d. I mixed 6 atomic orbitals to get 6 hybrid orbitals. Those 6 hybrid orbitals spread out in such a way that the electron domain is octahedral. So that is in the octahedral family, right? The electron domain is octahedral shape, but because we have 1 atom missing, this shape is square pyramidal. All of these 3 molecules have the central atom as sp3d2. Okay, and you could practice drawing the orbital diagram if you want, right? But now we would have 6 hybrid orbitals. So that's a lot, okay? By now, if you rewatch the video, take notes, you should be able to tell me all the hybridization states for the central atoms for all of these examples. There is more to hybridization because we also know that carbon can have a double bond. So let me just write it here in the corner. That is not sp3 hybridized because that carbon has only 3 balloons. The other issue is that we have a double bond. All the examples we did in this video have single bonds. So this is the topic of the next video. What kind of hybridizations do we get if we have to deal with double bonds and triple bonds? Question mark. So that's the next video. All right. Still going to use valence bond theory, but now we're going to use valence bond theory after hybridization to give us access to double bonds and triple bonds. And I'll show you how to do that.